Welcome to Oscillations. Today we're going to discuss the frequencies of free vibration and normal coordinates. Previously we have seen that equation 611 represents a good oscillatory solution for a set of n frequencies omega of index k. So then a complete solution to the equations of motion involves a superposition of oscillations with all allowed frequencies. For a small displacement around equilibrium, a system of n degrees of freedom will undergo small oscillation with the corresponding frequencies going from omega 1 to omega n. And the roots of the circular equation in this case are often called the frequencies of free vibration or the resonant frequencies. So as such, we can write the general solution for the coordinate, let's say eta I, as a linear combination of the components of the eigenmodes multiplied with the corresponding oscillation and a scaling factor. So now one has to keep in mind that for any given root of the circular equation, one has in fact two frequencies, one being positive and the other negative. So we could consider a solution written in this form. However, only the real part of the complex function is involved in the actual solution to the physical problem, and in both cases the real part always has the expression here. So it's just a cosine where the amplitude of k multiplying it and the phase contained in its argument follow from initial conditions. And as such, the initial form, the one given in equation 635, is the most convenient for manipulations. Now, if we take this expression at t equals 0, we can obtain the initial value of the coordinate as a sum of the real parts of over the products here. And if we also take its time derivative, we can find that the initial velocity, the initial generalized velocity corresponding to this coordinate, is given likewise by a sum of the imaginary components of the products here. So these constitute 2 times n equations for which these scaling factors can be evaluated both for the real and their imaginary parts. And then if we look at 647, for example, we can write this as a matrix equation for this is the vector of the initial positions, and it has to be equal with the matrix of the eigenvectors multiplying the real part of these scaling factors. And then we can do some very simple manipulations. We can multiply this with the product between the transpose of A and the kinetic energy matrix. And we do this because then if we apply the congruence of T for the matrix A, we get to immediately get to the result here. So the real part of the scaling factor corresponding to a given to a given component of the motion has the expression here. And similarly, we can obtain the imaginary component as well, just for the exact same argument, and we get the expression here, where I've written the sum explicitly to make it clear that in this case we are not summing over L, so we are just summing over the indices J and K. The two results we just obtained allow the calculation, this shouldn't be here, so allow the calculation of the complex scaling factors C and as such of the amplitudes and phases if we know the initial conditions, the matrix D of the kinetic energy and the matrix A of the eigenvectors of the problem. And the solution for each coordinate, as given in 645, is a sum of simple harmonic oscillations in all of the frequencies omega of index k, which are allowed by the circular equation. Unless we're in a situation where all frequencies are commensurable, that is, they are rational fractions of each other, then eta I will never repeat its initial value, and as such it is not a periodic function. However, one can transform from eta to a new set of generalized coordinates that are all simple periodic functions of time, and these are the normal coordinates. So we can write the etas as a linear combination of these zeta normal coordinates, or if we want to write this, we can cast this as a vector equation, as a matrix equation in effect, in the form here. Now remember from 6.4 that the potential energy is given by this particular contraction. Then if we take this result, so 642, together with the adjoint of this equation and the congruence transformation of V, we obtain that the potential energy is just the quadratic form shown here, where we have an implicit sum over the k index. Similarly, if we use result 6.10, we can write the kinetic energy as this kind of contraction, and using its own congruence transformation, we can obtain the kinetic energy itself as a quadratic form of the shape here. So what we see is that when mapping the problem in normal coordinates, both the kinetic and the potential energy are sums of squares without cross terms. And this is another way of saying that the matrix of eigenvectors A performs a principal axis transformation. In the case of the inertia tensor, the principal axis transformation was performed in order to reduce it to a sum of squares, the new axis being the principal axis of the inertia ellipsoid. Now, in our case, both the kinetic and potential energies are quadratic forms, just as the inertia tensor was, and they are both diagonalized by the matrix of the eigenvectors. So in effect, what we have done throughout the formal discussion of this problem is to perform a simultaneous diagonalization of two quadratic forms. If we now write the Lagrangian in terms of normal coordinates, then we can immediately derive the equations of motion, which just correspond to simple harmonic oscillators and small oscillations, and each of them will have the basic general solution given here. So each normal coordinate is a simple periodic function involving a single resonant frequency. And that is why they are also known, so these normal coordinates are known as the normal modes of vibration. All particles in each mode vibrate with the same frequency and phase, relative amplitudes being determined by the coefficients A of indices j and k. Weighing modes with appropriate amplitudes and phase factors provides the complete solution. Harmonics of the fundamental frequencies are absent from the solution due to the requirement for small oscillations and for the potential to be a quadratic form. The complete motion for small oscillations is obtained from exciting various harmonic oscillators with different intensities and phases. To put things in a broader perspective, this is the same kind of phenomenon that happens when we quantize the electromagnetic field. So in that case, the omegas of index k are photon frequencies, and their amplitudes become the occupation numbers in Fock space. So the number of photons in each mode for a given frequency. So hopefully, much later, we will be able to discuss this in more detail. For now, as a summary, we have decomposed the complete solution of the problem of small oscillations in a linear superposition of normal modes, that is, in simple periodic functions involving a single resonant frequency. And we have seen that the coefficients of this superposition are amplitudes and phase factors that determine the overall motion. In the following, we are going to apply these developments in order to discuss the free vibrations of the linear triatomic molecule. So, with all that being said, I want to thank you very much for watching. I hope you found this discussion worth your time, and I will catch you later. Goodbye.